Hello and welcome to another video tutorial about FreeCAD. In this video tutorial we are going to talk about outer threads. We are going to look at several screws and how to model them, for an example, and we are going to have a look at the workflow of Groove tool in the part design workbench, and we are going to have a look at the workflow of the linear pattern tool in the part design workbench. The version of FreeCAD I'm using here is the 0.15 stable release on a Windows 7 64-bit system. As already explained in the tutorial about the inner threads, when it comes to modeling screws and threads in 3D, as far as mechanical engineering is concerned, we often use an abstract representation of a screw. Like for instance here, or like here. Because on first look you can see it is a screw, in this case it has a hexagon head, and well, you can use of course your measurement tools within 3D to get an idea about the size and the length of the screw. And of course you have, like with the inner threads, more means to model a thread in 3D. As for example, you could use a concentric groove and a linear pattern in this case, but you don't have to design some sort of tooth profile along here. And of course you can try to model a real thread as far as you can go within 3D means by using a swept profile along a helix and then do a Boolean cut on the solids to get your thread. When it comes to modeling a screw in 3D, for example, you can do it like this. In this model, I have used in the part design workbench two operations: a revolution for the basic profile and a pocket operation for getting this hexagon slot. So if I have a look at the sketch of a revolution, you can see here the basic profile getting revolved at 360 degrees to get a shape like this, and then I just drew my hexagon sketch here on this plane and said I wanted to use the pocket operation, and that's it. The same idea was applied at modeling this screw. As you can see here, I also used revolution and pocket from part design workbench to obtain a shape like this. So in this case, this was the profile to be rotated at an angle of 360 degrees, and then I choose this face here and applied a hexagon and a circle sketch on this. Like you can see here, this is the hexagon and this is the circle, and then I applied a pocket operation to get rid of, let's say, the outer material here, to obtain the final shape like this. Of course, at least some of the shapes can also be obtained by using the part module workbench. Within 3D CAD, there is no golden rule how to model an object, and you will quite often find yourself looking at the model you already obtained and deciding, well, maybe it's the best to delete the model you already have and start all over again using a different design approach. So now I'm going to show you how to obtain a hexagon socket screw by using the part module workbench. So first of all, I'm going to close all those windows and I'm going to start a new document. So first I'm going to switch to the part module workbench. I'm going to insert a cylinder. I will highlight the cylinder in the tree view here, and I will apply with the data view a radius of 3 mm and a 8 of, let's say, 40 mm. I will now insert a second cylinder, giving it a radius of 5 mm and a 8 of 6 mm. Switching to axometric view, saying fit all. I am now going to highlight the second cylinder here, and I'm going to apply a placement to it. I will change the Z value to 40 mm to get the head here. I say OK, and now I will mark these two cylinders here, and I will apply a fusion to make a union of the two shapes. Now for this hexagon socket, I'm going to select this upper face here. I will switch to the sketcher workbench and apply a sketch to this face here. I will create a regular polygon. I will select the center point here and a point here. I will now select this point and the vertical axis here, and I will say I want to use the constraint fix a point onto an object. Okay. I will apply the same here, and now I will select these 2 points and this axis and apply symmetry. This could be one possibility, or I can say I want to make this point and this point coincident. This will result in the same situation. So now we have only 1 degree of freedom left. So if I select these 2 points and apply a horizontal dimension of 5 mm, we have a fully constrained sketch, and that's it. We are done with the sketch. It is not absolutely necessary to every time fully constrain a sketch, but it is good advice to do this, because if you leave an under-constrained sketch, that might lead to errors and misinterpretation in the future. So we will close the sketch. We will switch back to the part module workbench. We will do an extrusion. As you can see here, we want to extrude along the negative Z axis. So either we could apply here a -3 for -3 mm, or we could apply a value here in length, which is the same result. We will create a solid, and we do not want to be conical or something like that in some way. We don't want to apply a taper. So we say OK. And now if we highlight Fusion and extrude and we apply a Boolean cut, we have our socket here. Now we can apply a radius if we like, or to say a fillet of, in this case, well, we'll choose 1/10 of the diameter of the bolt of the screw. So in our case, we choose a diameter of 6 millimeter. So we will apply a fillet here of 0,6 millimeter. I say okay, the fillet is applied. And now I will apply a chamfer here. And the problem, or let's say the restriction with the chamfer operation in part design and part module is that, at least at the moment, there is only a chamfer operation with 45 degrees possible. So if you need another angle, and when we try to model realistic, we are facing the restriction that a metric thread uses an angle of 60 degrees. It is not possible to apply a chamfer of 30 degrees with this operation here. So in this case, I apply a chamfer of, let's say, 0,5. It's just an optical representation. And I'm done here. So this is another way of doing this shape here for this screw. And as you can see here, I use quite a lot of operations. Within part design, as you could see, I only used 2 operations, which was a little bit faster and is more parametric. If I want to use another length, in this case, I have to change the length, or to be exactly 8 of this cylinder here, and then I have to apply another Z value to the head here to get a correct shape again. Within part design, I would just have to change the value in the revolution sketch, and that's it. That's one of the big advantages of using part design over part module. Now for the version with a concentric groove and the linear pattern, I will start in part design workbench with a new document. First I will apply a sketch to the YZ plane. I will use the polyline tool to roughly outline the basic rotational shape of the screw. So I will sketch here the rough outline of the head, head back to the origin, and that's it. Now, as often, FreeCAD assigned here 2 constraints conflicting each other. So I have to delete one of the constraints, and the solver, as you can see, issues now no warning. Everything is okay. So first thing we will do is to create a fillet. We'll click on the icon. We will click on a point here and a point here. And FreeCAD automatically creates a fillet here with tangential constraints and everything else needed. I will do right click to end this operation. The next thing is to constrain the whole sketch. So first of all, since in a metric thread we have an angle of overall 60 degrees here, we will need an angle of 30 degrees here, or in other words, an angle of 150 degrees here. So I'll apply here an angle constraint of 150 degrees. I will also apply a radius constraint here of 0,6 millimeters. I will apply a vertical dimension constraint here, and the value is 2,385 millimeters. I did look in the instructions for the metric threads before creating this tutorial, so I looked all the values of all dimensions to be able to create real dimensions like this one here. So now we apply to these 2 points a vertical dimension constraint of 3 millimeters, since we want to do in this case a thread of 6 millimeters. I will also apply a 8 to the head of the screw of 6 millimeters. I will drag the line a little bit downwards to be able to apply a radius of 5 millimeters to the head. And now I will apply a horizontal length constraint of 40 millimeters for the bolt, or to say the shaft length here, and everything is constrained. I will close the sketch, apply a revolution. I will switch to horizontal sketch axis, and the basic shape is done. Now we will apply this hexagon socket. We will select the face here. We will apply a sketch to the face. We will change to the polygon sketcher tool. We will apply a hexagon here. And then we will select this point here and this axis here, and we will fix the point on the axis. We will repeat this operation here, and we will apply a symmetry constraint to these 2 points and this axis here. So we choose symmetry, and we are left with 1 degree of freedom. Of course, that's the basic size of the hexagon. So I will choose 5 millimeters for this dimension here. I will close the sketch. I will apply a pocket operation, and the length should be 3 millimeters. So overall, I'm done now with the basic shape of the screw, and will now continue with the groove. Unfortunately, the groove tool needs a flat face for its basic sketch, and since we have a revolved feature here, we don't have a flat face to apply a first basic sketch to. So we will do a trick, and the trick is that we select the front face here. We will apply a sketch to the front face here. We will select a rectangle here. We will apply equality constraint to these 2 sides. We will also apply a dimensional constraint of, let's say, 5 millimeters. We will close the sketch, and we will pad the sketch to 5 millimeters. As you can see, we just did an additional operation, providing us a flat face for the basic sketch we need for the groove. So the next operation is to select this front face of this cube here, or it is in fact a pad, and we apply a sketch, and we will apply with the polyline tool a triangle here. We will apply a horizontal constraint to this line here. We will apply equality to these two lines. And now we will apply once more a vertical constraint, a vertical dimension constraint of 2,385 millimeters to this point here. We will apply also a vertical dimension constraint of 3 millimeters here. And when I close the sketch for one moment and I toggle the visibility of the pad to have a better view of the sketch and to be able to work a little bit better. The next thing is we will apply an angle constraint here of 60 degrees. And now we need to position the sketch in Y direction. As you can see, the sketch is under constraint. If I click on a line here, I can drag around the sketch. So the next thing is that we should apply some construction geometry. So I'm applying these two lines here. I will mark these two lines and apply construction mode to these two lines. And I will apply equality constraint here to this line as well. And then I will select this point here, this axis here, and I will put the point, or I will fix the point to this axis here. I will close the sketch, and if I toggle the visibility, you will see this is the first groove, and I will apply the groove operation to the horizontal sketch axis. I will click on OK, and we just made the correct groove. We will need this cube also to define an axis for our linear pattern, which I will now define. So I will make sure that the groove is selected here. I will apply a linear pattern feature, and I will apply to an overall length of 23 millimeters. As you can see, transformation succeeded. FreeCAD did already 2 occurrences on a length of 23 millimeters, but I will have 23 occurrences. And that's how FreeCAD does here this operation. I will click on OK, and that's it. So all we have to do now is cut away this cube we just inserted as a helping feature, and when we are done. So I will select, in this case, this face. I will apply a sketch to the face. I will create an edge linked to external geometry. So I will select this edge here. I will create a rectangle, selecting a starting point, this point here. Because then I can fix this point on this point. Oh, sorry, this was the wrong constraint. Coincidence is needed. And then the next operation will be to set equality to these two lines, and the sketch is fully constrained. We close our sketch, we do a pocket operation, We say through all. We click on OK. And the screw is done. As you can see, visually, it really looks a little bit like a thread. So this is a commonly used trick if you want to do rendering with high quality and good looking pictures of your part. You normally don't use helix threads because that would mean a lot of CPU usage and a lot of calculation power, and so a lot of time to calculate a good looking picture. In most cases, a concentric groove with a linear pattern or something like that will be sufficient enough for these cases. So now we will start with the helix thread, and therefore I will just delete those features, and I will also delete those remaining two sketches. And I just realized I will also have to delete the pad. Okay, so this is our starting shape. As you may remember, we started with our revolution, and when we did our pocket operation to obtain this hexagon socket here. So now we will start with inserting the helix and the sweep profile and everything like that. Okay, so now we switch back to the part module workbench. We insert our helix, so we choose here helix. The pitch is 1 millimeter, the 8 should be 26 millimeters, the radius should be 3 millimeters, angle is 0 degrees, coordinate system is right-handed, that's okay. But the location we will change a little bit. The position is okay, and the direction should not be the Z direction, the direction should be the Y direction. As you can see, looking at the triad here, this is the Y direction. Okay, so we choose create, and we just see that the helix is inserted correctly. We choose close, and then our next thing is to create the sketch to be swept, so this triangle. So the next thing is to go back to the sketcher workbench or the part design workbench, and we will create a new sketch on the YZ plane, and then we will create our triangle here, and first thing we will do is create an equality constraint and applying it to these two lines. We will then apply an angular constraint of 60 degrees to these lines. We will also apply a vertical dimensional constraint in regard to the origin of 3,1 millimeters, and we will apply another vertical dimensional constraint of 2,385 millimeters to this base point of the triangle here. We close the sketch, and we are done. So the next thing is, when I click an empty space to make sure everything is deselected, we switch back to the part module workbench. We choose the utility to sweep, and we will do a double click on the sketch 002. As you can see, it is now here highlighted. We click an empty space to deselect everything again. And to get to a sweep path, we will do a double click on this helix here. If we do a double click, we will select the complete helix. If we only click once, we will select only the first turn of the helix. So we click on Done. We want to create a solid, not a shell object, and we want the threaded option to be true. This is to make sure that the beginning phase and the end phase of the sweep operation are coplanar. So I click on OK. As you can see here, the helix sweep was done correctly. And now I apply a Boolean cad on these two shapes. And here we go. We toggle the visibility of the basic sketch. And we also toggle the visibility of the helix. And as you can see here, we are basically done. But one thing remains. As you can see here, we end up in the middle of the material with our sweep and cut operation. So the main question is there something we can do to improve this situation? And yes, basically you have two options here. The first option would be to do a sketch on this face and apply a pocket operation to get a straight ending here. The second option would be to insert another helix, this time with an angle applied, so that you will get a swept and cut helix, which will leave the material at some point. But as you will see, FreeCAD basically can do helix operation, but its main geometric core is very weak on such operations. We will have to cheat to do, at least with a 0.15 stable release on Windows 7 64-bit, to achieve the correct result with these operations. If you will try a pocket operation here, FreeCAD will issue an error and will refuse to do the operation. So we do cheat, we do the sketch, and we do not pocket it. We will pad it and then apply a Boolean operation, which will result in a nearly correct shape in the end. And when inserted the second helix, if you will apply the correct dimension, in this case the correct dimension of this base point here in regard to the origin, which was, as you may remember, 2,385 millimeters, this helix operation, when applying the Boolean cut, will fail as well. That's why we will apply a little cheat there as well by changing the value to 2,386 millimeters, and then the Boolean operation will succeed. So now I'm going to show you all these two operations. So for the first idea, we will unhide this shape here. We will switch back to the part design workbench. We will create a new sketch, this time on the YZ plane. We will sketch out our basic triangle, making sure that this line is horizontal. We will apply equality to these two lines, and we will also apply an angular constraint of 60 degrees to these two lines. We will choose a base point of a triangle applying a vertical dimensional constraint of 2,385 millimeters. We will apply a vertical dimensional constraint to these 2 points of 3,1 millimeter. And we will also apply a horizontal dimensional constraint of 26 millimeters to the base point of the triangle in regard to the origin. We will close the sketch. We will apply our pad operation, leaving the length to 10 millimeter, choosing symmetric to plane. Okay. And then we will toggle the visibility of the basic shape here once more. And then we will apply our Boolean cad to these 2 shapes. So I will switch to the part module workbench, apply my Boolean cad, and that's it. So as you can see, these lines remained because we did a pad operation symmetric to plane. This is the cheat that did the trick. Because if we would have padded only in one direction, in this case in the X direction, we would have ended up with an error, just like if we would try to do the pocket operation. So as you can see, sometimes we have to cheat because FreeCAD is quite weak on helix-based operations. You may succeed with older or newer FreeCAD versions. It is sometimes a question maybe of a little bit luck, and maybe sometimes you just have cases with a relationship between your geometry constraints that is good, and sometimes you will have a situation where it is a bad relationship between your constraints, leaving the basic core being unable to perform the requested operation. So sometimes, as you can see, you have to use some small dirty tricks to cheat a little bit in FreeCAD to achieve the result you want to have. So let's have a look now at the second possibility by inserting another helix. So I will delete the cad operation and I will delete the pad operation, and I will leave the sketch here in place, and then I will insert the helix and do my sweep and my Boolean cad. Okay, so let's insert another helix. We will leave the pitch at 1 millimeter. The 8 we will leave at 2 millimeters. We will change the radius to be 3 millimeters. We will change the angle to be 20 degrees. And we will change the location and direction in 3D space. As you may remember, we ended up with 26 millimeters in Y direction. So we choose the Y value to be 26 millimeters and the direction to be Y as well. So we click on Create and then Close. And as you can see here, the helix operation was done successfully. We click in empty space to make sure everything is deselected. We click on the utility to sweep. We double click on the sketch 003 to make it a sweep profile. We click in empty space again to make sure everything is deselected. We click on sweep path. We make a double click on the helix to select the whole helix. We click on done. We want to create a solid and we want the threaded option to be true. We click on OK, and this is how the sweep operation is done. And then we will perform a Boolean cut on these two shapes. As you can see here, FreeCAD will not perform this operation successfully. So as I told you before, we will go back and try a little cheat, changing this value to be 2,386 millimeters. We click on OK. We will wait a little bit for FreeCAD to perform the operation. And as you can see here, our cheat did the trick and the helix operation is done successfully. As you can see here, this is how the end of a thread does look like now. Speaking of mechanical engineering, not in case of screws, but mostly in cases where you will cut the thread yourself to mechanical parts, there is also the option to have a groove at the end of the thread. A groove with an inner diameter of less than the inner diameter of the thread, so that the tool used to machine the thread will end up in empty space at the end of the thread. So with this, we reached the end of the video. I hope you enjoyed watching it. I hope also that I could show a lot of new things. And well, have fun with FreeCAD and maybe see you in another video. Bye!